Oh, hi. Today we will talk about the starting methods and operating modes of induction machines. So just to do a quick review and give an example, I would like to show you an application area for induction motor. So here you see an aircraft carrier of the United Kingdom. It's called HMS Queen Elizabeth, and actually that ship is propelled by, I think, 4 induction motors, and one of these looks like that one. So it is a 20 megawatt induction motor. So those are connected to propellers of the ship to drive the system. So many of you may think those large ships are driven by some maybe large diesel engines, but that is not the case. Many modern ships, not only warships but normal cargo ships and something like that, so they have their own, can be diesel generators, gas turbine generators, and then actually it is like a electrical distribution system. So those ships generate their own electricity and usually utilize them to drive the propeller by means of a induction motor. So this is a 20 megawatt induction motor. So just to put in scale, the total electric consumption of our campus, Meti campus, is around 5 megawatt. Okay, so that itself actually consumes 4 times of the electricity consumed by the Meti. So actually it's not the only case, and here you see that 20 megawatt motors is actually just one of the 4 motors drives the ship. So actually the reliability is quite important. So there are like many parallel systems. So actually you can see like one of those motors is driven through 3 different transformers and that kind of controllers. And actually the energy is coming from, I don't know if you can see that, so it is coming from like 1 2 3 4 diesel generator. So these are 8.5 megawatt, these are over 11 megawatts. Okay, but these are just auxiliary. The main power is coming from like turbo generators. So it's like again using some fossil fuels to run a synchronous generator. So there's like 1 2 3 4 5 6 synchronous generator connected to each other through an 11 kilovolt 60 hertz bus. So it's kind of a infinite bus, and actually the total generation is over like I think 110 megawatts. So it is like over 20 times of the electricity consumption of Meti is generated through that chip. And again, it is used for other purposes as well, but many of them is this is one of them is like 20 megawatts, so 80 megawatt power out of the 110 megawatt is consumed by the induction motor. So again, you can see why the efficiency of induction motor, or why the control of induction motor is so important in such a case. So again, when I say induction motor, don't think like something small motors that you can lift in industry or in other applications. You can see like really large induction motors. Okay, so before continuing, I would like to make a quick review of the typical curve of an induction motor. And here we have the synchronous speed, and as it is a synchronous motor, the induction motors actually cannot generate any torque on the synchronous speed. So you have 0 torque here, and some slip, the maximum torque generated. But usually this is like overload case for many induction motors. So that's okay to run for a couple of minutes depending on the machine size. But normally the machines are running at a smaller slip. So let me show it here. So this is the normal rating range. Okay, and again, if you just connect your machine to the grid or to whatever AC voltage source that you have, it will generate some starting torque also, that's called the stall torque, and then as time it usually increases to a maximum value, then it converges to the operating time. Okay, so then what is wrong? Okay, in this case, okay, you can just plug in your induction motor directly to the grid, but what's wrong with directly connecting that motor to a constant voltage supply? Okay, so if you remember the equivalent circuit, again, not getting into details, but I think you can remember, was something like that. Have the parallel branches, that is really important. In the starting case, R1, JX1, R2, R2, JX2, R2 prime, and this was, remember, 1 minus S over S R2 prime. So the thing is, if you apply a large voltage just starting from here, and when the slip is 1, okay, so that behaves like 1 minus S divided by S, so this is like short circuit. Okay, so you have that kind of current, or even if it is, S is not like 0, but let's say it's something not, it's directly 1, but it is something like 0.99. Again, if you think about that, 1 minus 0.99 is 1% of the actual resistance. So that component here has actually a small resistance when the motor is just starting to rotate, okay, through that point. So then in this case, that series branch has its minimum value, and you have I starting current, which can be really large, compared to what you will get in a normal operation. Because in a normal operation, let's say slip is 0.05, then it is 1 minus 0.05, it's around 1, divided by 0.05, it's as if it's multiplied by 20. So that pad, that equivalent impedance pad, actually increases, so the current gets smaller and smaller. So the problem with directly connecting a motor to a constant voltage supply is the high startup current. Okay, high startup current, and that is can be like 6-7 times of normal operating current of a motor. Then 6 times of the rated currents means, if you think about the I square R losses, then those are proportional with square of the current. So when the current is 6 times of the rated value, then the heat generated in the stator coils will be 36 times of the rated value. Okay, so the machine can generate a lot of heat really quickly. Again, that is usually tolerated by the heat capacity of the motor. So if you just run the motor, and it will just reach to that point in a couple of seconds, maybe several seconds, but then the heat still will be limited. But somehow, if you just lock the rotor, or I don't know, if the load inertia is so high, so it will take several minutes until the motor reaches the rated speed, then that extra heat can damage the motor. Okay, and secondly, you can generate low sometimes or high torques. Okay, so then usually, here you see the current is like 5 times of the rated value, so the machine will generate 25 times more heat than in the stator coils. But that doesn't always mean that drawing like 5 times more current will convert to 5 times more torque, or 25 times of the rated torque. Why? Because again, if that component is small, remember, what we have here is actually, that is the mechanical power. So the torque is directly proportional with the power dissipated in this component. But as the slip is small, so does that component. So you drove really high currents, but that current doesn't translate into a torque, but it will generate quite a lot of heat in those resistive components. Okay, or I mean, even if can generate like more than the rated torque. Okay, maybe your rated torque is somewhere here. Sometimes you don't want your motor to accelerate really quickly in some applications. For example, I don't know, think you are in an elevator, so the elevator speed, you know, can go quite high, but once you want to go floor, you push the button, and first it accelerates slowly, then it reaches some speed, then it decelerates again slowly. So what happens if it just you know, suddenly starts? It will be really uncomfortable, or it will be the same for subways, metro. Okay, so those motors are capable of accelerating or decelerating the wagon quite quickly, but for passenger comfort you want to limit that. So that is actually a quite important motivation, and you can see many applications in different fields. So you want to control the startup current, and you want to control, in some cases you want to increase the starting torque, but in some cases you want to decrease the starting torque. So you have to have some kind of control. So today we will talk about a couple of fundamental techniques to limit those starting currents. Then we will discuss the operating modes of induction machines. Okay, so let's start what we can do through the source side. Okay, how we can control our source without modifying our induction motor. So the first thing that we can do is to use auto transformer. Again, unfortunately this year, you know, due to coronavirus, you couldn't do the experiments in the lab. So in the labs actually we have those kind of equipments, both for the, you know, transformer testing and motor testing. And the idea is, so you have some kind of input voltage, and the output actually can be controlled. Let me write it here. So is it is like a controllable turns ratio transformer. Okay, auto transformer. So you rotate that thing, and instead of generating 230 volts, you can get 50 volts AC at 50 hertz, or, you know, 10 volts AC, 100 volts AC. Then you change the turns ratio, and actually you can apply a smaller voltage during startup, and, you know, you can increase it as the machine speed increases. And remember, the torque was proportional to V square. Why? At the end of the day, again, draw it quickly. So we have that component 1 minus S over S R2 prime, and that current is I2 prime. I didn't draw the parallel branch, and the power, okay, was proportional to, remember, I square prime 1 minus S over S R2 prime. Output power or mechanical power is. So therefore you can see, like, oh, I want 1 square. Okay, so you can see the current magnitude is also proportional with the voltage, applied voltage here. So I can say, like, torque is proportional. Torque is proportional to square of the voltage. So that means if I halve the voltage, I can halve the current, and I can reduce the torque to 1/4 of it. Okay, so 25% of it. So you can, again, if your load doesn't require a high starting torque, if you want to limit the input current, input inrush current, if you can just half the voltage, then you will reduce the input current to half. You can even apply like 1/10 of the rated voltage, so those starting currents will be limited, but again you are losing most of the torque. Okay, and another that requires an external equipment. Again, it's okay for some smaller applications, but for large applications it's not really practical, because you need to put maybe a variac as big as and also as expensive as the motor itself, so that is not really practical. Another really convenient and cheap method is to use a Y delta switch. In Turkish is üçgen yıldız anahtarı. Okay, and the idea is, okay, so those can be used for delta connected machines. So if you have a delta connected machine, okay, and if the machine is normally connected like that, so here you are applying some line-to-line voltage, and that line-to-line voltage in delta connection, remember, so V line to line is equal V phase in this case. But somehow if I connect that machine itself, like in that Y arrangement, if I can change the per phase circuit, so you have like those terminals, and again I'm not going to get into detail, but you can see how those are connected by that kind of a switch. So if you have a modification, something like that, okay, so even if you have the same line-to-line voltage, so now here your phase voltage will be the square root 3, line-to-line voltage divided by square root 3. So you can say, let me write here, in normal operation, which is delta, right? So let's say phase current, right, phase voltage, and then you have phase current, then you have, let's say, torque, say starting torque. You just start that machine normally, what you will see is, let's say you will have line-to-line voltage and phase current, let's say it will be I0, then the starting torque will be T0. Okay, or let me write it like I delta. This will be the torque in delta connection. However, if you just Y connection, okay, is just for startup, so during startup, so you can apply, instead of line-to-line voltage, you can apply the line-to-line voltage divided by square root 3. Okay, then if that machine, like if that one is drawing, if you are applying less voltage, then it will draw less current, so it will draw less current compared to the current drawn in the delta connection, right? Then remember, the torque was proportional with the square of the voltage or current. Then you can say the torque in this case will be the square of that thing, so you can generate 1/3 of the current that you will generate with normal delta connection. So again, if you closely look at the switch here, so you start, that is connecting to your motor like that, and it is at 0, so the machine is stationary, so it's not energized. And before coming into the delta connection, first you need to pass over Y. So you just switch it on, so the motor is energized with less voltage, so it draws less current, so it just starts up. So as it accelerates, I don't know, you will hear the sound once it's at a steady state, operating condition, then you can again connect it to delta to its final operating point. Then after on, it is normally run with normal parameters, but you limit the starting current. Okay. So other more expensive and actually more accurate motors are using some power electronic circuits, and again, that kind of applications is really cheap, and you can see in conventional systems, but you have some kind of sensitive equipment, or you want to control that kind of accelerations electronically, then you need to connect some kind of power electronics drives. So the simplest of those things are called soft starters. Actually, this is no different from the auto transformer method, but you are doing it, instead of doing with a transformer, you are doing it electronically using some switches. In this case, it's thyristors, and we will talk about those things. If you are interested, we will talk about those things in the 4th year power electronics course. So anyway, so you apply with a small voltage, line voltage, then that device will increase the duty cycles of the switchings of those transistors or thyristors in this case. So you keep increasing the line voltage up to its rated value. Once the machine reaches to its normal operation case, here you have like some kind of bypass contactors, so you can directly connect your machine to grid, and that device will cut itself out from the circuit. Okay, so these are soft starters. Those function is just to limit the starting current and torque. But if you want to control induction motor speed after it's started, then you need to control, you need to use some kind of variable frequency drives, and we will talk about those things again in power electronics course, and also we will discuss the function of those things in control of induction motor. So here what you see is, for example, you have a 3-phase connection from that point, so that can be like 400 volt line to line, like 50 hertz normal grid connection. So what you are doing is, first you are converting it to DC, like probably you remember that kind of bridge converters for single phase circuits. So that is for a 3-phase circuit. So you rectify that signal, and here you have a DC voltage, so you don't have any AC signal anymore. So then using that DC, then that is called inverter. So that is a DC to AC converter. And you do that again, that's out the scope of this course, but you convert that DC to AC by using 6 transistors and their anti-parallel diodes. Okay, but then you can actually, that voltage is voltage is variable. Okay, and also you can change the frequency. So you don't have to just apply 400 volts at 50 hertz. Maybe you can apply 50 volts at 10 hertz, or you can apply 200 volts at 15 hertz. I don't know, depending on what is the right operating condition for the motor. Actually, you can adjust both voltage and frequency. So that's why they are called variable frequency drives, or in short, they are also called VFDs. Okay, you will probably hear that a lot in professional life. Okay, so if you, again, I just would like to give you an idea. So you have those switches. The idea is, if you just turn on the top switch here, you can apply the high voltage here, or you can turn on the bottom switch here, then you can apply the negative terminal of the DC. So depending on how much on and off you have, so you did the same things with I don't know, PWM controllers in DC motors. So you can control the duty cycle, and you can adjust the output of a DC voltage. So here it is the same, but the duty cycle is constantly changing. So it is like that. So technically, if you just connect your oscilloscope and you can look at like really high frequency, and it can be like tens of kilohertz, okay, so you will have that kind of varying PWM width. So whenever your sine is at maximum, you have the maximum duty cycle, or whenever it is around zero, it is 50% positive, 50% negative, so they cancel each other. And whenever it is negative, so you have the maximum duty cycles at the negative side of those square waves. Anyway, so technically you apply that high frequency PWM signal like a variable duty cycle square waves. But if you take the first harmonic of that thing, and again, you know, motors are mostly inductive loads, so they are like j omega L, something like that. So the RL load is like a low pass filter, so the motor itself filters out those high frequency components. So what you end up is having a maybe not perfect but near to perfect sinusoidal waveform. Okay, and by changing the duty cycles, the magnitudes, so you can apply whatever voltage that you require. And actually, you know, power electronics are becoming more and more common, and many applications which you require accurate speed or position control, then you have to use that kind of drive. So for example, in electric cars, robotic arms, other industrial applications, I don't know, even in your washing machines, air condition units, they all have that kind of drives. Okay, so here let's compare different starting methods. Okay, so here the green one is direct online starting. It's also called DOL. So direct online starting is you don't have anything, you just plug it into the grid and your machine starts generating some torque, reaches to the maximum torque point, and it converges to the operating point. Okay, and if you look at the speed, current versus speed, so at NR is equal 0, and here slip is equal 1. Okay, so rotor speed is 0. So in that case, you have the maximum current, which generates a lot of heat and maybe even trip your circuit breakers or that kind of thing. So that may not be preferred. So the green is the default method. So what you can do is then use a Y delta switch, and first you start with Y connection, and you have like 1/3 of the rated torque that you will get from the direct online starting. Then it starts, then after at that point you move it to delta connection. Okay, remember you start with 0, first Y, then you make delta connection, and it makes a big jump. So again, it may not be preferred for some applications. And again, if you look at the current, it just starts with Y, then you just convert it to delta, then it have again inrush current. I mean, depending on the application, it can be higher than that value, or in some cases loss, but then you have some kind of a ripple, but then the amount of that ripple is much shorter because your machine is already rotating, and again it converges to here. Then you can do soft starting. Again, soft starting, the characteristics of that can be programmed to the soft controller, soft starter hardware, and you can, you know, either start it with constant torque, or you can limit the inrush current, and it will again be a nice smooth current and torque. Okay, those are the methods. We will talk about the variable frequency drives in the other presentation. And there are other techniques that we can do. I mean, these are the methods, the starting methods that we can apply on the source side. Okay, we are not modifying the motor, but actually we can modify the motor itself. So how our purpose is to increase the starting torque, but we want to reduce the current at the same time. You can say it's feasible, not, or maybe let's have a look at those equations just to have some reminder. So this is, remember, the torque equation, and we have, again, remember that one is proportional with the current, I square current. This is the maximum torque. Let me draw it here. We have that kind of torque. So this is the S max T, and this is the T max value that you see here. So if you look again, you don't have to memorize that equation, but you want to understand that one. So the interesting thing is, yes, maximum torque is proportional to applied voltage, and we have seen that, but that maximum torque actually has no component if you look at here with R2 prime. Okay, R2 prime is not here. Then if you look at that one, the maximum torque point, I don't know, let's for slipwise, let's say this is 0, let's say this is 1, and for our case, let's say maximum torque point is around 0.2. If this is 0.2, and if I would like to move it to 1, okay, I want to somehow modify that circuit, so I would like to have higher starting torque. Again, this is not desirable for every application, but there are some applications that you want maximum torque during startup. Okay, the method to do that, as you can see, is if I can find some method to increase that R2 prime over here that will not have any effect on the maximum torque value, but it will actually bring the point where the maximum torque occurs to that condition. Okay, so actually your curve will be something like that as you increase R2 prime. Okay, so again, you know, that is that can be applied in different ways, but the idea is if I somehow increase the rotor resistance, then I can move that torque characteristics to the left hand side. Okay, so I can start my machine with a high starting torque, and as the machine accelerates, actually I can then reduce the rotor resistance and I can adjust where the maximum torque occurs. And actually you can try it yourself by using the link in the presentation. Okay, and the idea is, again, you can do it in a continuous way, as we will discuss, or you can maybe have a couple of discrete operations. So you can start your motor with a resistance like that, and here it generates a high torque, then it will come down, then you will switch into a lower resistance to that one, then it will jump into this torque characteristics, then it will come down, so then you will change it to another rotor resistance, so it will accelerate in a much quicker way. Again, it doesn't have to be in discrete steps like that. You can actually control that maximum torque point to correspond with the actual rotor speed. Okay, so maybe the first thing that comes to your mind is, okay, we can add an external resistance. So what's the point? Okay, yes, you know, that is easy for one rotor induction motors, And actually, I think that is the only advantage of wound rotor induction machines compared to squirrel cage induction machines. In wound rotor induction motors, so this is your stator circuit, this is your rotor, and remember, in the rotor there are some slip rings which you can bring those terminals to the outside, and you can connect some kind of external resistance, and you can control that external resistance to control the circuit. But how we can modify the R2 prime for squirrel cage induction motor? So because in those ones we don't have any slip rings, actually we don't have any terminals that we can connect inside to the machine. I mean, maybe you can put some switches or some external resistances, but how we are going to fit into the rotor and how we are going to energize those things. So these are not really maybe applicable, but they will not be technically or economically feasible. Okay, so what we can do is we can use a really fundamental magnetic and electrical property of the rotor bar currents. We can use deep rotor bars, utilize rotor resistance change with skin effect. So what does it mean? So remember, as for example, if your something like that, so this is your rotor, right? Something that, so this is your rotor, and inside of the rotor, and you have either copper or aluminum. These are rotor conductors. So at first, remember, let's say rotor speed is 0 and applied frequency is 50 Hertz. So rotor bar currents, it will be, so again, remember the train analogy. So the rotor is not rotating in the lock rotor case. So if we apply 50 Hertz current to the stator, so we will have 50 Hertz current. Okay, for example, if NR is equal, I don't know, for a 6-pole machine, let's say it is 900 RPM, and synchronous speed is like 1000 RPM, or you can say slip is equal 0.1. So Fs is still like 50 Hertz, but in this case rotor bar currents, it will be, slip is like just 10%, so the motor itself will be rotating at 45 Hertz. Okay, so the rotor bar currents will be 5 Hertz, so compared to 50 Hertz, so now it dropped to 5 Hertz. Okay, again, if you remembered from the first semester with the skin depth, as the frequency gets higher, the current in a conductor tends to flow through outside. Okay, so at first it will tend to at 50 Hertz. Okay, so maybe it will just pass through that shaded area of the rotor bars, but then it drops to 5 Hertz. Then when it gets down to 5 Hertz, then the skin depth will be much larger, then you will have more homogeneous distribution in the rotor bar currents. Then if you compare the area on the red and the green ones, then you can see the equivalent resistance in the green area is equivalent area is higher, so that means the resistance will be less. So R2 prime is actually, if you just consider the, again, we don't have that kind of parameter in our equivalent circuit, but actually if you analyze it magnetically and if you design your slot bars properly, then you will see your R2 prime is not a constant parameter, but that's a function of the frequency. So R2 prime gets smaller as the rotor bar current's frequency gets lower. Okay, so actually we can, utilize that kind of things. And again, this is outside the scope of this course. We have some motor design classes in the graduate level, but what you can see, there are some classes, probably you will hear that, like class A motor, class B, class C, class D, whatever. And then those actually classes are dependent on the rotor shape. So this is, let's say, a normal shape. So you have like typical curve of induction motor torque. So it can generate up to like 150% of the rated torque. Okay, but however, if you, again, I think we are missing here, will be something like, they're called deep cage motors. Okay, so if you have some kind of, again, they have like really thin connections, or they have double cage, or like they have, like in this case with a deep cage motor. So if you have that kind of rotor shape, like as I explained here, for example, those can be isolated as well. So at startup, just one portion of the rotor bar is utilized, or let's say class D. So that creates a lot of torque during startup, maybe 3 times of the rated torque. And again, it converges down to here. So again, depending on the application, you don't choose the motors just depending on the like number of poles, rated power, rated speed, but also that kind of starting characteristics can be important too. Okay, so now let's move on to the complete torque characteristics. Okay, so up to now we just considered the points where the slip changes between 0 and 1, or where the rotor speed is changing between 0 RPM to synchronous speed. Okay, but can it be larger than 1, or can it be less than 0? And at the beginning of the induction machines, actually we discussed that one, and we showed yes, it can be. So here you see a complete torque characteristics. So here it is the speed in percent of the synchronous speed. So this is rotor not rotating. Okay, so this is rotor at synchronous speed. So in this case, this is the slip. So it is 1 slip, 0 slip, and we have seen we have that kind of configuration, right? So again, if somehow, for example, if the synchronous speed is rotating at 50 Hertz at one condition, and if my rotor is rotating at the same speed, then there's no voltage induced in the rotor. And then if my rotor is not rotating, and if my stator is rotating at 50 Hertz in one direction, then we are at that point. Okay, but then what happens somehow if I rotate the rotor in the other direction, then still I have my applied stator still in the going direction. So actually they are moving in opposite directions. Okay, so that is shown by like minus 20% synchronous speed, but synchronous speed is in the other direction. So that means, for example, you put your electric car in the dry mode, you want to go uphill, but your motor, your electric car is loaded so much, so even if you are in the forward gear, it starts going backwards. Again, in a practical application, that cannot happen. You have some brakes, other things, etc. But that means you want to rotate the rotor in one direction, but actually you have some kind of really large load torque, so it rotates the machine in the other direction. Or you have a crane, you want to lift something with the crane upwards, but you put again too much mass, so even if you want to pull the crane up, okay, it will keep going down. So in this case, you are in this region that is called the braking region. We will talk about that when the slip, so here slip is less than 1, larger than 0. Here slip is larger than 1, and in this region, okay, we'll talk about that one. So here it is slip is less than 0. So that means, okay, so you are at the synchronous speed, okay, your rotor and stator are rotating exactly at the same speed, but you don't generate any torque. Okay, somehow if you apply some external load, okay, if you start driving your motor, so you are not using mechanical energy, but you are supplying your mechanical energy, then you can accelerate your rotor even further. And as it accelerates, for example, if your synchronous machine is synchronous speed is 1500 rpm, then your rotor is now starting rotating at 1600 rpm. So now it is faster than the synchronous speed. So now the rotor current sees a slower AC signal. Again, I don't want to get into real magnetics equations, but our equivalent circuit can still model those things. We will solve a couple of examples. In this case, actually the power flow direction changes because we are not using mechanical energy, but we are giving some mechanical energy, or let's say you are connecting a wind turbine to the grid using some induction machine. So some wind blows up, so it tries to accelerate your rotor, and it starts accelerating. And again, as it goes higher and higher, okay, for torque, again, remember power is torque times omega. So the power flow direction has changed. So the speed is still in the same direction. So the torque direction has to change, so I can operate as in a generator. Okay, so in this case, again, they are not perfectly symmetrical, but you can assume to be symmetrical. So in this case, you will have more or less this mirror of that image over the horizontal axis. Then if you could just accelerate, you will reach to some maximum torque point in the generating mode. And again, if you go further, the torque will start decreasing. So for motoring mode, remember we were operating through that range, and for the generating mode, similarly, we will be operating at small slip values, okay, in this range. And technically, again, it is the same analogy with the synchronous machine, the same with the DC machines, okay. The generating mode, generators or motors are not two separate devices. Generating or motoring is just an operating mode. So the same machine can be run as a motor or as a generator. So actually that is what makes electric cars really efficient, because in normal internal combustion engines, once you accelerate, you already converted that energy to kinetic energy, then you don't have any means of methods to recover that energy back to gasoline or fuel, right? But in electric cars, even if you convert it, if you are going at 90 kilometers per hour, yes, you converted that energy to kinetic energy form, but if there is a red light ahead, then you put your foot on the brake pedal, then at first they don't apply the mechanical brakes immediately. Okay, so what they do is the variable frequency controllers adjust the operating modes, then your electric motors becomes generators. So now it is applying some negative torque, so it is slowing down your car, but while doing that you are charging your batteries in the generating mode. Okay, so that is the same analogy with the synchronous machines. Remember, in the synchronous machines, the motoring and generating mode depends on the loading angle. So whichever is leading the other, if the rotor is pulling the stator MMF or the stator is pulling the rotor MMF, then you will be in the motoring or generating mode. In the DC motors, remember, you have the back EMF, EA, you have the terminal voltage, and if that terminal voltage is higher than the back EMF, EA of a DC motor, then energy flows in that direction. If it is less than EA, then the energy or the current flows in the opposite direction. And in the induction motors, if the rotor is rotating slower than the synchronous speed, then you are in the motoring region. Or if it is rotating faster than the synchronous speed, then that means you are operating in the generating mode. Okay, again, we will come back to that topic in the control of induction machines. So here are, three different concepts, and again, braking can be also considered as generating or motoring. I will give you some examples. So in the motoring mode, let me go here. Again, this is your motor induction machine in general. Okay, so you have your shaft and you have your input power, right? So in this case, slip is less than 1 and higher than 0. So that means rotor speed is less than synchronous speed but larger than 0, right? So in this case, the input energy is coming like that, and you have some losses, P loss. Okay, those can be the copper losses in the stator winding, copper losses in the rotor, core losses, other maybe friction losses, etc. So then you have the P out, which is P mechanical. So energy flow is in that direction. So this is the electrical side, this is the mechanical side. Then if you are in the generating mode, okay, if you are in the generating mode, then that means, so this is again induction motor. So slip is less than 0. So that means rotor speed is larger than the synchronous speed. In this case, you are applying some mechanical power. Okay, think of the wind turbine. So the wind turbine blades generates some torque. So the power is getting into the machine, but you still have the losses. Okay, you have the heating and other things, etc. So because I'm telling that, because in some cases, the efficiency definitions, you can say, okay, input power divided by output power. Okay, that's fine. But if you just memorize the efficiency equations like electric power divided by, mechanical power divided by electric power gives the efficiency. Yes, that is true for the motoring case, but if you divide the mechanical power by the electric power in this case, okay, so you will have efficiency is larger than 100%, which is not correct because mechanical energy is now your input. You still have losses. These losses are not adding up, so it's still dissipating. So you have some electric losses. Okay, so be careful about those energy flow directions. And for braking, again, this is kind of interesting. For slip is equal to 1, that means rotor speed is less than 0, so it is rotating in the opposite direction. So if it is rotating in the opposite direction, so remember, so here like we have power is equal torque times omega, and torque direction is reversed, so the power direction is reversed. So in this case, we have torque times omega. Okay, so we still have positive torque, but our speed has reversed. So that means this one is like positive, but in this case this is negative. So that means power flow or mechanical energy is in that direction. That machine is trying to slow down. Okay, so technically it is, if you look on that side, it is the same way as in a generating mode. So that's why that's called the braking mode, or again similar to DC motors, we can call it the plugging mode. Again, this is not normally preferred. It can be some transient, it can be some emergency cases, that kind of things. You don't want to run your motor in the plugging mode continuously. Okay, the interesting thing is your motor is still connected to the same grid, and in this case the electric power is coming in that direction as well. So that energy plus that energy combined is actually transferred to losses. Okay, so you are consuming electricity and you are consuming mechanical energy, and then you are converting both of these energy to electrical energy. So at the end of day, again, we will start discussing it in the next lecture. So you generate, that kind of torque, or again, it goes like that. And let's say this is torque motor. Okay. So on top of that, you can have, I don't know, let's say you have like that. Okay, so this is some kind of load. Maybe it is constant, maybe it's not. And again, what you need to do is you are generating some electrical torque, and your machine requires some kind of load that can be in the forms of some weights. I don't know, maybe you are doing some other work. But then the difference, again, you have the friction, those can be added to load, or you can consider them other thing, but those load and friction are tries to slow down the machine, and electric torque would like to accelerate the rotor, and you take the difference. Okay, you take the difference, and the difference actually is some kind of conservation of energy. So you have some extra energy, and where does that extra energy goes on? This is inertia, so it either accelerates or decelerates. Okay, in this case, our the green arrows shows that difference. Ignore the friction for this case. So you have that amount of extra torque. So you can then, if you have a high inertia, your machine will start increasing its speed slowly. Then in this case, you will have maybe larger difference, so it will accelerate even quickly, then will come down slowly, and it will converge to a speed. And at that point, again, I neglected the friction for this case, so the motor torque and load torque are equal to each other. So whenever you have 0 is equal j d omega over dt, so j is not 0, so d omega over dt should be 0. That means in this condition, speed is constant. Okay, or somehow if you are operating at that condition, okay, then that means you have negative torque, so d omega over dt will be negative. Negative d omega over dt means your machine is reducing its speed. Its derivative is negative, so it's reducing its speed. Okay, so again, if you look at all those things, and we will talk about the active control, and again, I assume that topic will be clear after you completed your next set of assignments and experiments. But Similar to DC motors, we did it in the first semester. So we can define the operating mode in 4 quadrants. That's called the 4-quadrant mode. The first one is the torque is positive or clockwise, speed is clockwise. So in this case, let's say positive, torque is positive, so that means power is positive. Let's say you are giving some power to the output, so that means you are motoring in one direction, motoring clockwise. So in this quadrant, third quadrant, you have speed negative, okay, and torque is negative. So if both of things are negative, you still have some positive power, okay. So that means you are still producing some mechanical energy, but in the opposite direction. You can drive your car forward, or you can drive your car in reverse, but in each case you are converting electrical energy to mechanical energy. In the other generating mode here, speed can be positive. Instead of rotating at 1000 rpm in synchronous speed, let's say 6-pole machine, maybe you are running at 1100 rpm. So your speed is positive, but in this case your torque is negative because you are coming below. Let me go back. So let's say you are operating somewhere here. Torque is negative, but speed is positive, right? So if you operate in this case, so that means your power is negative, so you are converting mechanical energy to electrical energy. And similarly, in this case, let's say you apply how you make it rotate in the opposite direction. Again, you couldn't do it in the labs, but instead of applying ABC phases, you can reverse the sequence. Instead of applying ABC, if you apply ACB, then your rotating MMF will rotate in the opposite direction, so you can have other direction speed. And in this case, torque will be positive, and here power will be negative as well. Again, I think those operating modes will be much clearer once we talk about the control of electrical machines in the next lecture. Okay, thank you.